Somewhere out past everything you've ever known, a machine no bigger than a small car is drifting through territory human eyes have never touched. No probe has ever gone this far. No equation, no simulation, no theory has ever managed to predict what's actually waiting out there. And this isn't some sleek new piece of engineering fresh off a production line. It's a relic, built before the internet, before home computers, before most of the people currently poring over its data had even been born. It runs on 4 watts. 4. The bulb inside your fridge pulls more juice than that. And this fragile, decades-old, criminally underpowered machine, a machine engineers expected to lose contact with within 5 years, is right now beaming back data that's cracking open decades of physics. These scientists reading that data aren't calling it curious or unusual. They're reaching for words like astonishing, baffling. We had it wrong. This is Voyager 1's story, a story most people assume they already know, and almost nobody actually does. And almost nobody is telling it the way it deserves to be told, because it isn't just about what this spacecraft discovered out there in the dark. It's about how that discovery loops back and touches every living thing on this planet. It's about what's unfolding with this machine right now, in 2026, that barely anyone outside a small NASA lab even knows about. And it's about a date already carved into the calendar, a milestone no human civilization has ever brushed up against before. Keep reading. Once you know this story, you won't glance up at the stars the same way again, and you'll understand exactly why this particular clock is ticking down faster than most people realize. Rewind to September 5th, 1977. A rocket tears off the launch pad at Kennedy Space Center in Florida, hauling a spacecraft named Voyager 1 into the sky, watched by a handful of engineers who had no idea they were about to start a 50-year conversation. The plan is unglamorous. Fly by Jupiter, fly by Saturn. Snap a few pictures, take some readings, then coast off into silence. Engineers gave it 4 years, maybe 5. NASA figured the whole thing would be wrapped up by 1981 or 82, a tidy little postcard from the outer planets, then nothing. That is not how it went. Somewhere along the way, this mission stopped being a mission and turned into something closer to an act of sheer defiance. Every projection said it would fade out quietly. Every projection was wrong. Voyager 1 had other plans. It swept past Jupiter in March 1979, capturing humanity's first close-up look at that planet's surface. It swung by Saturn in November 1980, using each planet's gravity like a slingshot, gaining speed and distance with every pass instead of slowing down. Before the 1980s were even over, it had already outdistanced every object humans had ever launched into space, and it was still talking, still beaming its faint signal across an ever-widening gap, still gathering data, still humming along on hardware that would make a modern engineer's jaw drop. Then, in 2012, 35 years after launch, the story exploded in scale. Voyager 1 crossed the heliopause. If that word means nothing to you yet, here's why it should. It marks the single most important boundary in our cosmic backyard. Crossing it is the equivalent of walking out the front door of everything humanity has ever called home. Picture it like this. Our sun isn't just a source of light and warmth. It's constantly firing off a stream of charged particles known as the solar wind. That wind blasts outward in every direction, inflating a massive protective bubble that wraps around our entire solar system. Every planet sits inside that bubble. Every moon, every asteroid, every comet, every spacecraft we've ever sent up, every organism that has ever lived. All of it cocooned inside. The outer skin of that bubble, the exact spot where the solar wind finally loses its punch and gets pushed back by the pressure of interstellar space bearing down from the outside, is called the heliopause. That's the true physical edge of our solar system. Cross it, and you're somewhere else entirely. In 2012, Voyager 1 broke through that skin and kept going. It became the first thing humanity has ever built to physically leave the solar system. Not a symbolic milestone, not some technical footnote, an actual tangible object sent by us, now sitting in the space between stars. And it kept sending signals home. Pause on that for a second. There is, right now, a working scientific instrument parked in interstellar space. Not skimming the outer solar system, not hovering near the boundary, genuinely inside the cold, ancient dark that separates star systems, a place no telescope, no satellite, no theoretical model built on Earth has ever been able to study from within. And it's telling us what that place is actually like. What it's saying is nothing like what anyone predicted. And this is exactly where the story stops being a nostalgic footnote about an old spacecraft and turns into something that should genuinely rattle anyone who trusts our best scientific models of the cosmos. Long before Voyager 1 arrived there, physicists spent decades constructing elaborate mathematical models of interstellar space. These weren't wild guesses. They were rigorously tested, peer-reviewed frameworks built by some of the best minds in the field. And virtually all of them agreed on the same basic picture. Interstellar space should be calm, thin, cold, a sparse nothing where particles drift lazily along and not much ever happens. Basically a quiet waiting room between solar systems. Voyager 1 stepped into that waiting room and found a full-blown storm instead. Starting in 2017, its plasma wave instrument picked up something no one had anticipated and no one could immediately make sense of. A steady, narrowband signal. A quiet but constant hum buried inside the interstellar plasma that, according to every model on the books, shouldn't exist in that form. This wasn't a one-time spike you could write off as noise. It was continuous, year after year, spanning a stretch of interstellar space over 900 million miles wide. For comparison, Earth sits just 93 million miles from the Sun. This hum has been tracked across a distance 10 times greater than the gap between our planet and our star. That silence is coming. The exact day isn't locked in yet, but the trajectory absolutely is. Every year, the power drops a little more. Every year, another instrument goes dark. Every year, the JPL team faces tougher calls about what stays on and what gets sacrificed, knowing there's no reset button, no backup mission, waiting in the wings to pick up where this one leaves off anytime soon, and no way to explain to future generations exactly what it felt like to have a live voice out there. However faint, however slow, however easy to take for granted. Sometime in the early 2030s, the last instrument will hit its minimum threshold. The final signal will begin its 24-hour trip home, arrive, and get recorded. Somewhere. A room full of engineers who've poured entire careers into this one spacecraft will watch that last transmission land, knowing there will never be another. A strange kind of grief for a machine, but a grief that will be entirely real for the people who spent decades listening to it. And after that, nothing. Voyager 1 will simply keep moving, silently, at 38,000 miles an hour. Carrying its golden record deeper into the dark, drifting through regions of the galaxy, human eyes won't reach for tens of thousands of years, continuing a journey that started on one ordinary September morning in 1977, when a handful of engineers aimed a machine at the stars, pressed a button, and figured it would last 5 years. Here's what deserves to stick with you. Buried in the middle of all this is a fact easy to lose sight of amid the physics and the engineering drama, a fact that deserves way more attention than it gets. Right now, in 2026, the only functioning scientific instrument humanity has ever placed in interstellar space is 48 years old. Older than most of the people keeping it alive, older than the internet, older than color television in most households. It runs on technology that predates personal computers. It's powered by less electricity than the bulb over your kitchen stove. And it's sending back information that is actively rewriting how we understand the universe and our place inside it. Since then, we've built bigger machines, more powerful ones, projects that cost exponentially more and use exponentially fancier technology. None of them have told us what Voyager 1 is telling us right now, because none of them had the one thing the spacecraft has, the sheer stubbornness to keep going long enough to actually arrive. Budget and horsepower were never the missing ingredient. Time and distance were, and only this machine has both. Some questions about the universe simply can't be answered from the outside, no matter how sharp our math gets or how massive our telescopes grow. They can only be answered from inside it, not from a ground-based telescope, not from a satellite circling Earth, not from a mission to Mars or the asteroid belt, only from a machine that physically crossed the heliopause and stepped into the space between stars. We have exactly one such machine, just one, in our entire history as a species. It's old, it's fading, and it's running on 4 watts. And as long as it keeps transmitting, we need to keep listening, because when it finally falls silent, some of the biggest answers we've ever chased fall silent right along with it. At least for a generation. The signal is still coming, stretched across 15 billion miles, delayed by 22 hours of raw travel time, carrying word of a universe that's stranger, more turbulent, more interconnected, and more extraordinary than any Earth-built model ever managed to capture. A universe that had been quietly waiting for someone, anyone, to actually go check. Think about everything riding on those 4 measly watts. 50 years of engineering choices made by people who could never have pictured 2026. A recording of human sound and music built to outlive our species, our cities, quite possibly our entire planet. A live, ongoing correction to the physics textbooks, delivered in real time by a machine nobody expected to survive its own decade, let alone become the single most important scientific instrument operating outside the solar system. 4 watts, doing the work of an entire field of astrophysics. Out past the edge of everything we've ever called home, that machine is still drifting, still transmitting, still turning up things nobody predicted, in a place nobody's ever been able to check before. It was never built to chase headlines. It was built to do a job, and it just hasn't stopped doing it, decade after decade. Breakdown after breakdown, watt after dwindling watt, long after everyone who launched it assumed the story would already be over. One machine, 4 watts. One shot to listen. The only real question left is whether anyone's actually tuning in. For decades, models of the heliopause predicted a smooth, gradual handoff. Solar wind fading slowly on the inside. Interstellar material slowly becoming detectable on the outside. A gentle blend at the edges, like a river easing quietly into the sea. That's not remotely what Voyager 1 encountered. At the heliopause, particles weren't calmly dispersing. They were smashing into each other at speeds brushing up against a meaningful fraction of light speed, generating temperatures close to 30,000 degrees Celsius. Not inside a star, not anywhere near the sun. At the outer rim of our own solar system, in a zone that was supposed to be cold, thin, and unremarkable. Some researchers now describe this region as a wall of fire, and they aren't speaking poetically. They mean a literal physical concentration of blisteringly energetic charged particles forming a real barrier at the very edge of home. Then came the magnetic surprise, and this one might top everything else. For decades, one core assumption about the heliopause was that the magnetic landscape would shift sharply the moment you crossed it. Inside, the sun's magnetic field. Outside, a completely separate galactic magnetic field. Two distinct systems, cleanly split at the boundary. Voyager 1 blew that assumption apart. The magnetic fields on both sides of the heliopause are, in ways no existing theory anticipated, tangled together. The sun's magnetic field lines, dragged outward by the solar wind and squeezed at the boundary, are interacting with the galaxy's own magnetic field through a process called magnetic reconnection, where field lines from two separate sources cross, rearrange, and release energy. Our solar system and the galaxy surrounding it aren't magnetically isolated from each other. They're linked. Right at the edge of everything we know, there's an active zone trading energy between our home and the wider cosmos, a process no model, before Voyager 1 got there, ever accounted for. This isn't some throwaway detail. This isn't a small correction bolted onto existing theory. If the connection between our solar system and interstellar space is more active, more entangled, and more energetic than the models claimed, then everything we thought we understood about how the heliosphere has shielded Earth across geological time needs a serious rebuild. Every simplified diagram of a neat, sealed bubble around our solar system just became, at best, an oversimplification, and at worst, flatly wrong. Textbooks written on the assumption of a clean, self-contained solar system just picked up a giant asterisk. Now fast forward to what's unfolding right now, actually in 2026, because this story is far from over. It may in fact be entering its closing chapter, and the timeline is tighter than most people grasp. Earlier this year, NASA made a call nobody on the mission team wanted to make. The low-energy charged particle instrument, one of Voyager 1's original science packages, gathering data almost non-stop since 1977, got switched off. Not because it broke. It was working perfectly fine. It got shut down purely because Voyager 1 is running out of juice, and there simply wasn't enough left to keep it powered. Voyager 1 draws its electricity from 3 radioisotope thermoelectric generators, essentially canisters of decaying plutonium-238, where the heat from that decay gets converted into electrical power. At launch, those generators cranked out roughly 470 watts. Today, nearly 49 years on, they're producing about 250 watts and losing roughly 4 more watts every year. Sometime in the early 2030s, the output will dip below the bare minimum needed to run even one remaining instrument. And Voyager 1 will go silent, permanently. The team has seen this coming for years. Long ago, engineers and scientists sat down and mapped out exactly which instruments to power down, and in what sequence, to squeeze the maximum possible science out of a shrinking energy budget. Of the 10 scientific instrument packages Voyager 1 launched with, 7 are already dark. Each of those calls is brutal because every instrument lost represents questions that will simply never get answered, and there's no way to flip one back on once you've decided you cut it too soon. Imagine sitting in a room, choosing which piece of a 50-year legacy gets sacrificed this year, knowing exactly what discoveries you're closing the door on forever. But here's the twist barely anyone outside the JPL team knows about. They haven't given up on stretching this out further. NASA engineers are reportedly working on something they've nicknamed internally the Big Bang procedure, an experimental attempt to rewire how power flows across Voyager 1's remaining systems, squeezing out extra electrical capacity from components currently running below their potential. It's technically dicey and genuinely risky, since even a small tweak to the power routing of a nearly 50-year-old spacecraft, with no manual override available anywhere, could trigger unpredictable results. So the team is doing exactly what careful engineers should, testing it first on Voyager 2, which has slightly more spare power and sits a bit closer to Earth, making a failed attempt a little less catastrophic and a lot easier to learn from, before risking the same move on its twin. Those Voyager 2 tests were slated for May and June of 2026. If the results confirm the procedure is safe, The same fix will be attempted on Voyager 1, with the earliest possible attempt targeted for no sooner than this July. Here's why that matters. If it works, there's a genuine shot at bringing the low-energy charged particle instrument, the one just powered down, back online. Nobody's making guarantees, but they're not giving up either, because betting against Voyager 1 has never once paid off. The spacecraft has been counted out before, mourned as a closed chapter more than once, and every single time it's found another way to keep talking. And now, the date already locked onto the calendar, a moment no human civilization has ever reached before, arriving whether or not the rest of us are paying attention. On November 18th, 2026, at 2:16 and 12 seconds in the morning, Pacific time, Voyager 1 will hit a distance of exactly 1 light day from Earth. That means a signal moving at the fastest possible speed the universe allows will take a full 24 hours just to arrive. Send a command Monday morning, and you won't even know it landed until Tuesday morning. You won't get the spacecraft's reply until Wednesday. 2 entire days just to complete one. Exchange of information. No human-made object has ever traveled that far. Not once, not the pyramids, not the moon landing hardware, not a single satellite or probe in the whole span of civilization. This one machine is about to outdistance everything else we've ever built. And it's doing it while it's still awake, still working, still talking back. And on that date, Voyager 1 crosses that threshold while it's still very much alive. Still transmitting, still reporting back. Then it just keeps going. Every hour, roughly 38,000 more miles into the dark, and every hour the round-trip conversation with Earth stretches a little longer, the margin for error a little thinner, the sheer scale of the distance a little harder for any human brain to actually hold on to. The delay keeps growing, the power keeps shrinking, and sometime in the 2030s, the final signal will arrive. Even then, Voyager 1 won't stop moving. There's nothing out there capable of stopping it. No friction, no atmosphere, no gravitational pull strong enough to meaningfully bend its path. It'll simply keep drifting in a straight line at 38,000 miles an hour into darkness with no finish line on any timescale a person could wrap their head around. No sunset, no horizon, just distance, endlessly compounding. And bolted to its frame, riding along on this dying machine is something built to outlast all of it, the Voyager Golden Record. A gold-coated copper disc carrying spoken greetings in 55 human languages. The sound of rain falling through a forest. The sound of ocean waves. The sound of human laughter. 90 minutes of music drawn from cultures spanning the whole of human history. Diagrams explaining the basics of our physics and math. A map built from pulsar positions, designed to show whoever eventually finds it exactly where in the galaxy our planet sits. Carl Sagan, who helped design the record, called it a message in a bottle tossed into the cosmic ocean. That's precisely what it is. Not a data package, not a scientific artifact, but a deliberate, hopeful gesture. A species reaching into the dark to say, simply, we were here. Whoever or whatever eventually finds that disk, some future civilization a million years from now, or a form of intelligence we can't even picture yet, it'll tell them something true, that there was a species here, that they were curious, that they reached outward, that they built a machine out of metal, electricity, and mathematics, and launched it past everything they had ever known, carrying the sound of their own laughter along with it. That record will still be drifting when the sun swells into a red giant and swallows Earth's orbit whole. It'll still be out there long after every human city, every archive, every name we ever carved into stone has been worn away by time and geology. It's the single most permanent object our civilization has ever produced. And it's riding on a spacecraft that currently runs on less electricity than the bulb above your bathroom sink. Now, back to the science, because there's one more thread here that deserves center stage. That persistent plasma signal Voyager 1 has been tracking since 2017 isn't just some anomaly. Researchers describe it as the first continuous, real-time measurement of interstellar plasma density humanity has ever managed to collect. Before this, scientists could only grab occasional snapshots of interstellar plasma density, measurements triggered by rare events like shock waves from massive solar eruptions that traveled all the way out to the heliopause and rippled beyond it. Useful, but scattered, like trying to understand the weather across an entire continent using one thermometer. Us in one city, checked once a year. And what Voyager 1's steady signal delivers instead is closer to a live feed, a continuously updating portrait of interstellar plasma, built day by day, year by year, as the spacecraft physically moves through it. And that portrait shows us interstellar space isn't a flat, featureless backdrop, not the empty hallway between star systems that generations of physics students were taught to imagine. It has texture. It has weather. It has structures made of charged particles and magnetic fields stretching for millions of miles, interacting with the edge of our solar system in ways no Earth-based model could ever detect or forecast. The space between the stars isn't empty. It's full. It's active. It has a physical personality. Humanity is only now, for the first time in our history, beginning to actually decode. There's one central question here that scientists still haven't cracked. That persistent emission has two possible explanations, and researchers combing through the Voyager 1 data still can't say for certain which one is correct. Possibility 1. It's thermally excited plasma oscillations, natural vibrations of plasma particles reacting with their surroundings. That would still be a genuinely major discovery, but it would fit neatly inside existing physics frameworks without forcing anyone to tear them down. Possibility 2. What Voyager 1 is picking up is something called quasi-thermal noise, an entirely different physical mechanism, one that encodes plasma density and temperature information in a subtly but critically different way. If that's the real answer, our current models of the interstellar medium need a serious overhaul. Settling this requires either more raw data from Voyager 1 itself, which is producing less every year as more instruments go dark, or an entirely new mission, purpose-built to study interstellar space with instruments designed from the ground up for exactly this job. No such mission currently exists. None is currently funded. Even if construction started today, it wouldn't reach the heliopause for at least another 25 years, meaning an entire generation of scientists, and probably an entire generation of the public, will grow up without a single live instrument inside interstellar space. Which means that once Voyager 1 finally goes quiet, this question stays wide open. The map it started sketching stops getting filled in, and the only real-time window our civilization has ever had into interstellar space slams shut, and stays shut for decades, maybe longer, depending on whether anyone with the funding ever decides this gap is worth closing. The team studying this signal, in a paper published in the peer-reviewed journal Nature Astronomy, didn't soften the conclusion. Interstellar space, they said, is nothing like the placid, uniform void the models promised. It's turbulent. It has structure at every scale imaginable, from gaps you could measure in meters up to distances stretching across millions of miles. In a very real sense, it's alive, buzzing with motion and complexity. We simply couldn't see before because we'd never had a single instrument sitting inside it. Let that sink in. Every model of the space beyond our solar system was constructed from the outside, from a planet, using telescopes and math and theory. And now, the first instrument we've ever actually parked inside interstellar space is telling us those models left something huge on the table. The universe past our solar system is messier, more dynamic, and more intricately structured than anyone realized. And here's where this quits being abstract science and starts hitting closer to home. None of it stays out there. It reaches all the way back to us. The same bubble separating our solar system from that chaotic interstellar zone is the exact bubble shielding life on Earth. The heliopause isn't just a line on some diagram, it's armor. It blocks the most dangerous cosmic radiation, the high-energy particles hurled out by exploded stars light years away, keeping them from slamming into the inner solar system at full strength. If that shield turns out to be weaker or less predictable than we assumed, the stakes for life on this planet are enormous. And what Voyager 1 is showing us is that the interstellar environment pushing against that shield from outside is rougher, more erratic, and more energetic than any existing model accounted for. We still don't know exactly what that means for the long-term durability of the shield itself, but simply having to ask the question marks a real shift in how we think about our own species' vulnerability. A shield we assumed was rock solid and well-mapped turns out to be facing down a far angrier ocean than we ever modeled. That alone should be dominating headlines. It almost never does. And the plot only thickens from here. Because before we even get to what Voyager 1 found right at that boundary, we have to talk about 2023. The year Voyager 1 nearly flatlined them. For 5 straight months, the spacecraft kept transmitting a signal back to Earth. But the signal was garbage, corrupted, scrambled, unreadable. Even to the engineers at NASA's Jet Propulsion Laboratory, who had spent decades decoding everything this machine had ever sent. The instrument was clearly alive. The transmission was clearly arriving. But whatever message it carried had turned to static. For a team that had run this mission flawlessly since 1977, this was uncharted territory. Nearly 50 years of steady, dependable contact, and suddenly the spacecraft was speaking in a language nobody on Earth could parse. A silence dressed up as noise. When engineers finally traced the cause, it was as simple as it was brutal. A single memory chip inside the spacecraft's flight data system had physically broken down after nearly 5 decades of relentless cosmic radiation exposure. One microscopic chip, sitting on hardware soldered together decades earlier, had developed a fault that corrupted the exact portion of software responsible for packaging and transmitting scientific data. No alert, no warning light. The chip had simply given out after 46 years of continuous operation in the single harshest environment any human-built object has ever endured. Under normal circumstances, when a piece of hardware fails, you send someone to fix it or swap the part or replace the whole unit. None of that was an option here. The failing component sat 15 billion miles away, completely unreachable by any transportation humanity has ever devised, with zero chance of a repair mission on any useful timeline. The only tool available was radio, moving at the speed of light. Even at that speed, a message took 22 hours just to reach the spacecraft. 22 hours there, 22 hours back. A minimum of 44 hours for a single round-trip exchange. Now picture what that actually meant inside mission control. Study the incoming data, build a theory, draft a set of test instructions, send them. Wait 22 hours. Receive whatever comes back. Pick it apart. Discover it's slightly off from what you expected. Build a new theory. Write new instructions. Send them again. Wait another 22 hours. Repeat that cycle, patiently, methodically, for months, all while knowing that one bad command, sent once across 15 billion miles of empty space, could kill the mission for good with no way to undo it. The JPL team pushed through this grind for months, carefully, under a level of pressure most engineers never encounter. All over, and they pulled it off. They realized the damaged code couldn't be patched, but it could be relocated. They broke the corrupted software into smaller chunks and moved each chunk into a different functioning section of the spacecraft's memory, checking and rewriting each piece so it worked correctly in its new home, then stitching it all back together into a working whole. This was essentially remote brain surgery carried out through a 44-hour communication lag, on a machine nearing its 50th birthday, sitting 15 billion miles beyond anyone's reach. No margin for error. No do-overs if a line of code landed wrong. Just patience, expertise, and month after grinding month of careful, nerve-shredding work. By mid-2024, Voyager 1 was back. Clean, readable, complete data started flowing again. And what did it immediately send back? More proof of those unexplained plasma oscillations rippling through interstellar space. More measurements of the very turbulence no model had ever forecast. A spacecraft that should have died in 1981 had clawed its way out of what could have been its final silence, and it came back with more secrets to share. But none of it, not the discovery, not the near-death scare, not the recovery, really prepares you for what Voyager 1 actually found the instant it crossed the heliopause back in 2012. This is the part where the science papers stop sounding like physics and start sounding like something out of a different genre entirely.